Across the vast expanse of the cosmos, a celestial ballet unfolds. Stars, the building blocks of galaxies, are not eternal. They are born, they evolve, and they eventually die. This cosmic cycle of stellar life and death is fundamental to the universe as we know it. At the heart of this cosmic dance lies a fascinating object, the protostar. These stellar embryos, shrouded in veils of gas and dust, hold the key to understanding the birth of stars and the evolution of galaxies. Protostars are celestial objects on the verge of igniting into full-fledged stars. They represent the earliest stages of stellar evolution. Think of them as cosmic seeds, pregnant with potential. Their study allows us to peer back in time to witness the very processes that led to the formation of our own sun and solar system. The study of protostars is not merely an exercise in cosmic archaeology. By understanding how stars form, we gain insights into the formation of planets, the evolution of galaxies, and the distribution of elements in the universe. Join me as we embark on a journey to explore these stellar nurseries where the seeds of stars are sown and the destiny of galaxies is shaped. Stars, unlike anything else in the universe, are capable of creating their own light. But where do these luminous giants come from? The answer lies in the cold, dark depths of space, within vast clouds of gas and dust, known as molecular clouds. These clouds, often spanning hundreds of light-years across, serve as the nurseries for starbirth. Molecular clouds are not uniform in their structure. Within these clouds there are regions of higher density, where the concentration of gas and dust is significantly greater. These dense regions, often referred to as cores, are the seeds of future stars. Gravity, the architect of the universe, plays a crucial role here. Imagine a cloud of gas and dust spread out over trillions of miles. Within this cloud, gravity acts as an invisible hand, pulling the material together. Over millions of years, these dense cores within molecular clouds become gravitationally unstable. They begin to collapse under their own weight. This collapse marks the first step in the extraordinary journey from dust cloud to protostar. The formation of a protostar is a majestic process, driven by the relentless force of gravity. As a dense core within a molecular cloud collapses, it begins to spin. This spin is a consequence of the conservation of angular momentum, a fundamental law of physics. Think of a figure skater pulling their arms in to spin faster. As the core collapses and spins, it heats up. The gravitational potential energy is converted into thermal energy, causing the temperature at the center of the collapsing core to rise dramatically. This hot, spinning core, still shrouded in a thick envelope of gas and dust, is what we call a protostar. At this stage, the protostar is not yet a true star. It is not yet hot enough to fuse hydrogen into helium in its core, the process that defines a star. However, the protostar is already emitting light. This light, however, is not from nuclear fusion, but from the heat generated by the gravitational collapse. Gravitational collapse is the engine that drives the formation of protostars. As a dense core within a molecular cloud collapses, the material within the core experiences an increase in density and temperature. This increase in temperature is crucial, as it provides the initial heat that will eventually allow the protostar to ignite nuclear fusion. The collapse of a dense core is not a uniform process. The outer layers of the core fall inward faster than the inner layers. This is due to the conservation of angular momentum. As the material falls inward, it conserves its angular momentum by spinning faster. This rapid rotation creates centrifugal forces that resist the inward pull of gravity. Think of a spinning ice skater. As the skater pulls their arms in, they spin faster. Similarly, as the material in a collapsing core moves inward, it spins faster, creating a balance between gravity and centrifugal forces. This balance is crucial in shaping the structure of the protostar and its surrounding environment. Section 5, a star's womb, the accretion disk. As a protostar forms, it is not alone. Surrounding the central protostar is a swirling disk of gas and dust known as an accretion disk. This disk is a consequence of the conservation of angular momentum during the collapse of the dense core. As the material falls inward, it cannot all fall directly onto the protostar. Instead, it settles into a disk-like structure, orbiting the central object. The accretion disk is more than just a cosmic byproduct. It plays a crucial role in the evolution of the protostar and the formation of planetary systems. The material in the accretion disk is slowly spiraling inward, feeding the protostar and increasing its mass. This process of accretion is what allows the protostar to grow and eventually reach the mass required to ignite nuclear fusion. Imagine a whirlpool, with water spiraling inward towards the center. The accretion disk around a protostar acts in a similar way, channeling material onto the growing protostar. This process of accretion shapes the destiny of the protostar, determining its final mass and influencing the formation of planets around it. Section 6. Stellar Tantrums, Outflows and Jets. Protostars are not passive recipients of infalling material. As they accrete material from their surrounding disks, they also launch powerful outflows and jets of gas into space. These outflows and jets are a consequence of the complex interplay between gravity, magnetic fields, and rotation within the accretion disk. These outflows are not mere cosmic breezes. They can extend for trillions of miles into space, shaping the surrounding interstellar medium and influencing the formation of other stars in the vicinity. The jets in particular are collimated beams of gas that shoot out from the poles of the protostar. These jets are thought to be launched by the twisting and tangling of magnetic field lines in the accretion disk. Imagine a spinning top, with its axis wobbling slightly. The jets from a protostar are thought to be launched in a similar way, as the magnetic field lines threading the accretion disk twist and reconnect, launching material along the axis of rotation. These jets are a testament to the powerful forces at play during the early stages of star formation. Section 7. Cosmic Nursery's Famous Protostar Hotspots. The process of star formation is not unique to our corner of the universe. It is happening everywhere in galaxies near and far. Astronomers have identified numerous regions in our galaxy, the Milky Way, where stars are actively forming. These regions, often referred to as star-forming regions or H2 regions, are characterized by their abundance of gas, dust, and young hot stars. One of the most famous star-forming regions is the Orion Nebula, located in the constellation of Orion. Visible to the naked eye as a fuzzy patch in Orion's sword, the Orion Nebula is a vast cloud of gas and dust illuminated by the intense radiation from young, massive stars. Within the Orion Nebula, astronomers have identified numerous protostars, still in the process of formation. Another famous star-forming region is the Taurus Molecular Cloud, located in the constellation of Taurus. The Taurus Molecular Cloud is a much closer star-forming region than the Orion Nebula, making it an ideal target for studying the early stages of star formation. Astronomers have identified numerous protostars within the Taurus Molecular Cloud, providing valuable insights into the processes that govern the birth of stars. Section 8. Stellar Adolescence, the T Tauri Phase. As a protostar continues to accrete material and contract, its core temperature and density continue to rise. Eventually, the core becomes hot and dense enough to ignite nuclear fusion, marking the transition from a protostar to a true star. However, before reaching this milestone, the protostar goes through a phase of intense activity known as the T Tauri Phase. T Tauri stars are young, variable stars that exhibit strong stellar winds and intense magnetic activity. They are named after the prototype of this class, T Tauri, located in the constellation of Taurus. During the T Tauri phase, the protostar is still surrounded by a disk of gas and dust, but this disk is beginning to dissipate due to the intense radiation and stellar winds from the central star. The T Tauri phase is a critical period in the life of a star. It is during this phase that the star's magnetic field interacts with the surrounding disk, influencing the formation of planets and shaping the environment around the young star. The study of T Tauri stars provides valuable insights into the processes that shaped our own solar system billions of years ago. Section 9. Protostars shaping the universe one star at a time. Protostars, those stellar embryos hidden within cosmic clouds, are much more than just celestial objects. They are the engines of cosmic evolution, shaping the universe we see around us. Their birth, fueled by gravity and driven by accretion, is a testament to the elegant laws of physics that govern our cosmos. From the initial collapse of a dense core within a molecular cloud to the ignition of nuclear fusion, the journey of a protostar is a story of transformation. It is a story of matter coalescing under the relentless pull of gravity, of energy transforming from one form to another, and of the emergence of complexity from simplicity. The study of protostars is not just about understanding the birth of stars, It is about unraveling the intricate web of cosmic processes that have shaped the universe we live in. It is about tracing our cosmic lineage back to the stellar nurseries where our own sun and solar system were born. And it is about inspiring future generations to gaze up at the night sky with a sense of wonder and a thirst for knowledge.